Summary. Let us summarize what we have learnt in this chapter. Mechanical waves can exist in material media and are governed by Newton's law. Transverse waves are waves in which the particles of the medium oscillate perpendicular to the direction of wave propagation. Longitudinal waves are waves in which the particles of the medium oscillate along the direction of wave propagation. Progressive wave is a wave that moves from one point of medium to another. The displacement in a sinusoidal wave propagating in the positive x direction is given by y as a function of x and t equals to a sine kx minus omega t plus phi, where a is the amplitude of the wave, k is the angular wave number, omega is the angular frequency, kx minus omega t plus phi is the phase, and phi is the phase constant or phase angle. Wavelength lambda of a progressive wave is the distance between two consecutive points of the same phase at a given time. In a stationary wave, it is twice the distance between two consecutive nodes or antinodes. Period t of oscillation of a wave is defined as the time any element of the medium takes to move through one complete oscillation. It is related to angular frequency omega through the relation. T is equal to 2 pi by omega. Frequency v of a wave is defined as 1 by t and is related to angular frequency by omega equals to 2 pi mu. Speed of a progressive wave is given by v, which equals lambda by t. The speed of a transverse wave on a straight string is set by the properties of the string. The speed on a string with tension T and linear mass density mu is V is equals to under root T by mu. Sound waves are longitudinal mechanical waves that can travel through solids, liquids or gases. The speed V of sound wave in a fluid having bulk modulus B and density P is V is equals to under root B by rho. The speed of longitudinal wave is a metallic bar is V is equals to under root Y by rho. For gases, since B equals to gamma P, the speed of sound is V is equal to under root gamma P by rho. When two or more waves travels the same medium, the displacement of any element of the medium is the algebraic sum of displacement due to each wave. This is known as the principle of superposition of wave. Y equals summation I is equals to 1 to n fi into x minus v into t. A traveling wave at a rigid boundary or a closed end is reflected with a phase reversal, but the reflection at an open boundary takes place without any phase change. For an incident wave, yi as a function x and t equals a sine kx minus omega t. The reflected wave at a rigid boundary is yr as a function x and t equals minus a sine kx plus omega t. For reflection at an open boundary, yr as a function x and t equals a sine kx plus omega t. The interference of two identical waves moving in opposite directions produces standing waves. For a string with fixed ends, the standing wave is given by y as a function x and t equals to 2a sine kx cos omega t. Standing waves are characterized by fixed locations of zero displacement called nodes and fixed location of maximum displacements called antinodes. The separation between two consecutive nodes or antinodes is lambda by 2. A straight string of length L fixed at both the ends vibrates with frequencies given. Mu is equals to Nv by 2L for n is equals to 0, 1, 2, 3 and so on. The set of frequencies given by the above relation are called the normal modes of oscillation of the system. The oscillation mode with lowest frequency is called the fundamental mode or the first harmonic. The second harmonic is the oscillation mode with n equals to 2 and so on. A pipe of length L with one end closed and other end open, such as air column, vibrates with frequencies given by mu is equals to 2n plus 1 by 4L for n is equals to 0, 1, 2, 3 and so on. The set of frequencies represented by the above relation are the normal modes of oscillation of such a system. The lowest frequency given by V by 4L is the fundamental mode or the first harmonic. A string of length L fixed at both ends or an air column closed at one end and open at the other end vibrates with frequencies called its normal modes. Each of these frequencies is a resonant frequency of the system. Beats arise when two waves having slightly different frequencies V1 and V2 and comparable amplitudes are superposed. The beat frequency is V beat equals V1 minus V2. The Doppler effect is a change in the observed frequency of a wave when the source and the observer O move relative to the medium. For sound, the observed frequency mu is given in terms of the source frequency mu naught by. Mu is equals to mu naught into V plus V naught divided by V plus Vs. Here, V is the speed of sound through the medium, V naught is the velocity of observer relative to the medium, and Vs is the source velocity relative to the medium. In using this formula, velocities in the direction observer to source should be treated as positive and those opposite to it should be taken to be negative. That's all in this chapter. Hope you have enjoyed it.